So we are almost finishing now the chapter 2 on PCA, and we've been looking at the question of how do we find the optimal number of principal components given a data set. We started in the last class by noticing that when we apply PCA to a data set, we make an error in the approximation, and that error depends on how many principal components we select. And the error has the following form: is equal exactly to the sum of the squares of the singular values of the data matrix, starting from the d plus 1, where d is the number of principal components that I select. And we did in the previous lecture a plot of what these singular values look as a function of the number of selected components. Sorry, actually I shouldn't have said this. This is a plot of the error. So this is the error. And we observe this phenomena that the more principal components I select, the smaller the error. And therefore the reconstruction error is not a good criteria for selecting the number of principal components. So the key question was how we're going to do to determine the number of principal components. So I started by looking at some simple criteria, which is to effectively observe that if we do expect the data to be low rank, we would expect to have a large error originally, but eventually we hope that the error will go down very quickly for the ideal optimal number of principal components that we should select. And so one way to do that is by looking at what percentage of the total energy contained in data matrix is preserved. And one criteria that we looked at was the following, which is perhaps one of the most commonly used ones, is to select D as the minimum D such that the error that is made from D plus 1 to D versus the total number of the total energy of the data, which is the sum of all of the singular values, so from 1 to D, is less than some threshold. Okay? So that is one of the most commonly used criteria. And we discussed a simpler version of it, which is simply just to threshold the singular values. Since the singular values are in decreasing order, we said just choose the first D such that the singular value squared is below some threshold. So those were some of the criteria we discussed in the previous lecture. So to do this in a slightly more principled way, the idea is essentially the following. This fitting error tells you how well the model fits the data. And of course, the more principal components, the bigger the model, the better I fit the data. And that's why it just keeps decreasing. So when trying to select what is a good model in terms of its dimension, we need to have some extra criteria that measures what is the complexity of that model. Okay? So a classical example that maybe you've been exposed in calculus is this question of, I give you data and maybe you want to fit a polynomial to the data. And should I use the polynomial of degree 2? Should I use a polynomial of degree 3? Should I use a polynomial of degree 20? So evidently, in that particular example, right, if I just have data and I was trying to fit a polynomial, as I increase the degree, right, suppose that actually I had, for the sake of argument, 10 points. If I keep increasing the degree, eventually with a degree 10 or 11, there's always maybe a tiny error there, you can actually fit the polynomial perfectly through the data, right? Eventually, the degree will be large enough that you can pass through every single point, right? But typically, that's not necessarily a great model, because what we want in machine learning is, we fit maybe the model, but we want that model to predict what's going to happen after it, or maybe a new data point is there and is very badly predicted. So that's an issue that in machine learning is called overfitting, that I have a model that is very complex, or it has way too many parameters, more than needed. And what we care about is the predictive ability of the model, not really the fact that in the data, it fits the data perfectly. So by analogy here, if I keep increasing the dimension of the subspace, eventually the subspace will pass perfectly through each and every data point in the data set. But that's not what we want. So how do we prevent that from happening? We prevent that from happening by penalizing the complexity of the model. So how do we measure complexity? There are lots of different ways by which I can measure complexity. And so we're going to go through a few of them today. But the basic idea of model selection at a very intuitive level is to say that I would like to effectively minimize, with respect to the dimension, in this case of PCA, some error, which depends on the, and this is the fitting error, plus, and maybe I'm going to have some parameter, the complexity. And the complexity somehow should be dependent upon the dimension. Okay. So the simplest notion of complexity, perhaps, that we can have is exactly the dimension of the subspace, right? So the dimension of the subspace, if I plot it here, it would be a straight line, right? It would just be D. Okay? And so if I now sum the error, which is what I have here, and the complexity measure, which in this particular case is just D, hopefully I'll get some curve that looks like this. Okay? And then I will be able to find the optimum D star, which is the right dimension. Okay? So let's do this, in particular here. How can we do it? So what we have been doing is minimize with respect to A, x minus A, Rene squared, such that the rank of A is equal to D. Okay, that was the rank minimization view of PCA. Right? So the idea is that we are, instead of enforcing the dimension to be known, what we're going to do is, following this paradigm, we're going to minimize, with respect to A, the error, x minus A, Rene squared, plus tau times the rank of A. Okay? So in that way, the idea is, given the data matrix, find another one that is close to it, as measured by the Frobenius norm. But instead of saying choose A to have a fixed rank D, this says among all possible A's, also penalize the rank of that selection. So we've seen already that if the rank of A is exactly equals to D, then that objective, which is minimized with respect to A, x minus A, Frobenius squared plus tau rank of A, exactly what I just wrote, I'm just repeating it. It's equivalent to, right, if I now fix the rank to be D, I'm going to put tau times D. And now, the minimum value for this first term, when the rank is fixed to be D, is what I already know from the previous lecture. So this is just the sum of sigma I squared of x from D plus 1 to D. And that is my function of D that I would like to use. Okay? So now I need to minimize with respect to d this function that I'm going to denote f. Okay. So in other words, in principle, this problem was somewhat messy because I needed to optimize over a matrix A, but also over all possible choices for the rank. But the beauty of the PCA theorem is that we know that for each fixed rank, PCA gives us the optimal solution. And the optimal solution is obtained from the SVD, as we have done over and over. So I can reduce the optimization from all possible matrices of all possible ranks to just optimizing over the rank, because for each fixed value of the rank, I know that the optimal solution is given by the SVD, and I know that the reconstruction error for a fixed rank is exactly given by the sum of the squares of the singular values from d plus 1 onwards. So this quantity now, it's a quantity that is discrete. For each value of d, I have a number. Okay? And it's exactly a little bit like this picture. It's like what I'm going to do here is now I'm going to evaluate it, evaluate it, evaluate it, evaluate it. Eventually I'll get to the minimum. And then it starts going up. Okay? So how do I find the optimum of this error? Well, what I would like, right, is for the following thing to happen. The optimum has to satisfy, again, look at that picture, right? When do I get to the optimum? I get to the optimum when, if I increase the rank by 1, the error starts to go up, right? You see that from the picture? If I increase the rank by 1. So, what needs to happen is that f of the optimum plus 1 needs to be bigger than f of d. Right? That's how I find the optimum d hat. It's the first time that the error goes up. And so what this means is that now I replace the error. This means that the sum from d plus 2 to d of sigma I squared plus tau times d plus 1 needs to be bigger than the sum of the sigma squared from d plus 1 to d plus tau times d. All right? And so, what I get is that tau needs to be bigger than the sum of the sigma I squared from d plus 1 to d minus the sum of the sigma I squared from d plus 2 to d. Right? Because look at what happens here. You have tau times d plus 1 minus, and move this to the left, tau times d, right? What is the difference between the two? Tau, that's what I put here. And that's bigger than this guy minus that guy. And that's all what I've done. And now this has the sum of everything from d plus 1 to d, and this has the sum of everything from d plus 2 to d. So what is the difference of these two? Huh? Sigma d plus 1 squared. Aha. So if I do this model selection business, and the way by which I penalize complexity is by the rank of the data matrix, or the number of principal components, if you wish, then the optimal solution for the number of principal components is just based on thresholding the singular values, which was one of the heuristics that I've written on the top, right? Okay? So that heuristic, that in the beginning was just a heuristic, actually is the optimal solution to some model selection problem. Maybe a super simple one, but at least it's not just a random way of selecting the optimal. Now, you could ask the question, is this a good choice or is it a bad choice? And I already commented in the previous lecture that it's not quite a great choice. And one of the reasons I gave was it's not invariant with respect to scaling the data. If I multiply the data matrix by 2, all of the singular values will be multiplied by 2, and then I'll need to change the threshold. Okay? So that's why the alternative criteria, the one that's at the very top, is better in practice. Because if you scale the matrix by a factor, then you don't need to change the threshold. Okay? Right? So, this is all great and it's all nice in principle, but I tell you, in practice it's not great, and you will always struggle with finding the number of principal components, because in the end of the day, what's really happened is that you are a little bit sweeping the problem under the rug, because rather than selecting the number of principal components, what you're doing now is selecting that threshold tau. And depending on the choice for tau, you will get a different number of principal components. Okay. Nonetheless, just as a matter of notation, let me introduce here something called hard thresholding. Which is simply going to be the following notation, which is x if x is bigger than epsilon, absolute value, or 0 otherwise. Okay? So basically, if you give me a number, if that number is large enough, you keep it. If that number is below a threshold, you set it to 0. Okay? And the reason I'm going to introduce that notation is because we're going to use it for writing down the optimal solution to PCA with model selection. Right? So if you recall, well, that's the optimization problem we're trying to solve, and the question is, what is the optimal solution? And we know that it's the SVD, right? So, so the solution to min x minus a radius squared plus tau rank of a, which is what we just discussed, is equal to a is equal to u hard thresholding with the square root of tau of sigma and v transpose, where x is equal to u sigma v transpose. Okay, so it's just a little bit of fancy notation, but we're going to be defining, moving forward in the next 2 or 3 weeks, many different thresholding operators. And so this style of writing things is going to become very handy. So that's what I'm introducing today in the simplest possible case. Okay, so I recall what you already should know. How do you find the optimal solution to the PCA problem? You take the data matrix, you compute the SVD of it, and then you keep the top D singular values, right? That's the way you do it. So that's exactly equivalent to what I just said, because see, if sigma had sigma 1, sigma 2, sigma little d, and then sigma capital D, right? If I apply the thresholding operator, the hard thresholding, then I'm only going to get the first D. And all others will be set to 0. That's the idea, that sigma is a diagonal matrix, so all the zeros are preserved by the threshold, and everything that is below sigma D, well, the idea is obviously that these guys here are bigger than or equal to square root of tau. Is clear this weird notation that I'm introducing? And is that clear? Yeah. Okay, good. Now, let me introduce other ways of measuring complexity, as well as relaxed versions of this. So let me begin with the relaxed versions of this. A disadvantage maybe of this formulation is the following. This piece is sort of a convex problem, but the rank is always a nasty thing. Okay, so this optimization problem as such is non-convex because of that rank piece. But we got very lucky. We were able to solve it in closed form. What we're going to be using, particularly in the next chapter, is that we're going to start replacing non-convex objectives by convex surrogates of those non-convex objectives. And so I'm going to introduce in particular one such non-convex surrogate, which is the so-called nuclear norm. So the nuclear norm of a matrix is the sum of the singular values of that matrix. Okay? And by the sake of comparison, notice that the Frobenius norm squared is equal to the sum of the squares. Okay? So, so one alternative way of doing model selection is to consider then minimize with respect to A, x minus A Frobenius squared plus tau times the nuclear norm of A. Okay, see what I'm doing? All I did was to replace the rank by this nuclear norm. By the way, I am saying a few things here that I haven't even proven or anything. Maybe you've never seen this nuclear norm before, and so you might immediately ask, why is it a norm? Good question. Then I said I'm going to replace the rank, which is non-convex, by this thing, which is convex. Why is it convex? Okay. So all of the questions that I'm just asking, those are the questions for homework number 2, okay? Which I already posted on the website. So one of the questions would be, have a look at the nuclear norm, show that it's a norm, show that it is convex, calculate the subgradient of it, and things like that, okay? And in particular, one thing that I'm going to ask you to show in the homework is the following. That the optimal A, so now this is homework 2 here, okay? In homework 2, you're going to see that the optimal A for this problem is given by U S of tau of sigma and V transpose. Where S tau of x is equal to x minus tau if x is bigger than tau and 0 otherwise. What does this mean? What is the intuition? What's really going on here? So you take any value. What did we do before? If it is above a threshold, we keep it. If it is below the threshold, we set it to 0. Hard threshold. Now what we do is the following. I am given a number. If it is above the threshold, I subtract the threshold from it. Okay? If it is below the threshold, I set it to 0. Okay? So this operator is called shrinkage thresholding, because you first shrink it by the threshold, and then you threshold. Okay? And so all I'm saying here is that there is this alternative to the right, alternative way of penalizing complexity, that interestingly enough ends up with a solution to the PCA problem, which is almost like PCA, but instead of keeping the top D principal components, actually you do keep them, but the singular values you shrink them a little bit by the threshold. Okay, so that was a second way of measuring complexity. Let me introduce a third one. In fact, there are many, but let me introduce a few. And actually, maybe let me build the intuition first. The intuition is what I was trying to say here. We need a way of measuring the complexity of the model that I'm trying to fit. So, if this was fitting a polynomial to data, it could be a degree. If this is fitting a subspace to data, I argue, let's use the dimension. Okay? But intuitively, it needs to be something a little bit better. It really needs to measure the complexity of the model. And so how do you measure the complexity of a model? Typically, a better way to do it is measure it in terms of the number of parameters that you're really fitting to the data. Right? And so when you fit a subspace to data, the dimension D evidently is a part of it. But it's not a good count of all of the parameters that are being fit. Right? And so how many parameters are really being fit when we do PCA? So if we think of a subspace, right? Let's just think of a linear subspace. We've parameterized a linear subspace as u times y for all y in Rd. So the parameterization of the subspace here really is the number of parameters that I'm fitting is more like the dimension of the data, and this is a D by D matrix, right? That's what it is. But in addition, I need to compute the low dimensional representation for each data point, correct? And that's the D-dimensional part. But I do that for each data point, correct? So the reality is that it is almost, what I'm doing is sort of factorize the data matrix X into the basis for the subspace, which is D by D, and the low dimensional representation, which is D by M, right? And so the number of parameters that I'm fitting is therefore D times D plus D times N, perhaps. Okay. Everybody with me? Okay. I was hoping to get a complaint at least that the counting is not right. Okay, so intuitively the counting seems reasonable, but any correction that I need to do?
Why is it plus?
Huh?
Why is it plus?
Why is it plus? Mm-hmm. Oh, because I am fitting a subspace to the data. And so for that, I need to compute D times D. But in addition, I need to compute the low dimensional representation.
But isn't the low dimensional representation based on the D that you're getting? Well, I guess my question is why isn't it multiplying?
How do I explain this? The way I see it is, okay, maybe I should explain it in simple terms. Suppose that I was fitting a line, y equals slope times x plus n. How many parameters am I fitting there? two. There is one for which is this and one that is that. Right? So by analogy, what I'm doing here is, if you recall, our model was x is equal to u times y. Right? Where x was known, but this is unknown and this is unknown. So the number of parameters that I'm fitting is how many unknowns do I have in this set of equations. And so every entry of u is unknown, and every entry of y is unknown. So I just need to add them. It's just counting how many unknown entries. Yes?
What about, once you know u, y is fixed, so there aren't really that many independent parameters. So intuitively it feels like it'd just be d times little d. All you need to know is u and then y. It's good.
But also with x.
Yeah.
But it doesn't work like that, because, right, it's like, imagine you're just writing a system of equations. You just count the number of variables that you need to solve for. Right? And sure, you're totally right that once I know one, I can solve for the other. But that doesn't mean that the number of variables I need to solve for has reduced when I start analyzing the problem.
Is everything in continuing on the same thing? Is everything on U is independent, and also are we assuming that it's an affine subspace?
In this particular case, I wrote this linear, but so that answers your second question. But your first question is the critical one.
Yeah.
Are all the entries of U independent from each other? And so what's the answer? No. Why not? Because the subspace is only defined up to a change of basis, right? So I can always insert a and A inverse in the middle, and this is a D by D matrix. Okay? So I just need to count the number of independent variables. So technically speaking, because of this, I should be subtracting a D squared from there. Okay. Analyze it. That being said, most of what has appeared in the literature for PCA, if you look at the way in which they have done the counting, let me give you a few of the existing criteria. So I'm going to write down 3 different criteria, and I'm not going to explain them in detail. So the anticipation information criteria. BIC. And this one does sum of the sigma I squared log n, and then d times d sigma squared. Then there is the Akaike. Sum of the sigma I squares plus times d sigma squared. That's the second one. And the last one is the geometric version. And that is sum of sigma I squared plus 2 times d times d plus n times d 6. And this is from d plus 1 to d plus 1 to d plus 1 to d. Okay, so let me just explain the very high level, because model selection is a topic that's been researched for a very long time. In fact, in the appendix of the book, you will find at least 10 pages on what model selection is about in general, the definition from a statistical point of view, and how it gets to be applied to probabilistic models. Okay? So this, I'm just going to cover here what the formulas are and a little bit of the intuition of where they come from. But if you really want to learn this subject in more detail, I encourage you to just look at the appendix. I think it's Appendix B, the statistical appendix. So, the first term is common in all three cases, and that is just the reconstruction error. Right? So going back to what's written here, right? That's exactly this term. Okay? So the only thing that changes is how the complexity of the model is measured. So in the case at the bottom, that should be the most familiar because that's the one we were just discussing. The way that the complexity is measured is exactly how many parameters are there in the model. And here they didn't do the counting exactly right because they didn't subtract the number of redundant parameters. But by and large, it's counting the number of variables needed to fit U and the number of variables needed to fit D. Okay? And as you can see, it's linear in fact in D, right? So this is exactly 2 times D, and now it's D plus N. So for a matrix of fixed size, where D and N are fixed, really it just grows directly linearly with D. So this last criteria effectively is the same as the one we were discussing here. Right? Where was it? This criteria. Right? You can immediately say, well, this is exactly what we just covered, and tau, in this particular case, happens to be chosen as 2 D plus N, and then sigma squared. What are all these variables? The interesting thing is that, as you can see, the threshold tau, rather than being chosen arbitrarily, like a constant that is the same for all matrices, the choice of the threshold depends upon the dimensions of the matrix. Okay, so it's D plus N. And then, there is this part that I have not explained, where it comes from. The idea really is that you have data that is sampled from a subspace, and then you corrupt it with noise. And the noise follows a Gaussian, and sigma square is the variance of that Gaussian. Okay. Why do you think this is important? Well, think again about this picture. If the data was perfectly of rank D, how would this look like? It would be here. It will go sharply down, and then be constant, right? So a matrix that is rank D and has no noise, we expect the behavior of this error to be like this, sharply go down. Okay. So what the reason for this extra stuff is really just that you add noise. And the more noise you add, the more this will go up, right? In fact, if you start adding a lot of noise to the data, eventually your singular values are just going to go down like that, right? And you're going to have a very hard time figuring out what is the dimension. So, as a consequence, the reason why that tau should grow with the amount of noise, right? If there was no noise, any threshold, any reasonable threshold would do the job. In fact, a threshold of 0, I could just say, look at the singular values of the matrices, the ones that are non-zero, those are the ones that you keep. But as you add more and more noise, you need to move up your threshold, right? Because you need, effectively what you're trying to do is to distinguish the singular values that come from the data versus the part that comes from the noise. So this is exactly what this is saying, that if you actually knew how much noise the data had, you should be adapting your threshold accordingly. All right? But again, this is all intuitive. Then, let me go back. This is the Akaike information criteria. As you can see, it's essentially the same. But it's only counting the number of parameters in the basis for the subset. We had the discussion before. Should I only count the basis? Should I count both? What is the number of unknowns? So here you have a criteria that only counts the number of basis elements. Okay. And then the Bayesian information criteria comes from the information theory literature that grew up around the 50s approximately, where you were trying to measure the amount of information in data based on the number of bits. And so that's why this logarithm shows up here, which is the logarithm of the number of data points. I am personally not advocating for any criteria, and I'm just telling you if you are asked the question, how do I find the number of principal components? I'm telling you, people have studied that question. There are criteria that exist for doing so. My practical experience is that no criteria is really great, and that determining the number of principal components remains a little bit of an art and an unstudied problem, except for the fact that some interesting theoretical results are starting to come. And so I'll present in a second one of the recent theoretical results regarding this matter. So what is that result? So this is a theorem. So the idea is, suppose that x0 belongs to this B by N matrix that is low rank. Suppose that I measure a corrupted version of that low rank matrix, which is written as follows. So I take the low rank matrix and I add noise, where E, the EIJs are IID samples from a Gaussian distribution that is zero mean and has unit standard deviation. Actually not, zero is 1 over square root of n. This version of the theorem for now would assume that B is equal to n, so the matrix is actually squared. So let x star be exactly U hard thresholding with parameter tau of sigma and B track. In other words, let's consider that solution obtained by thresholding the singular values for the matrix with some value tau. Okay? And now let's consider the error as measured as follows. Is the limit as the size of the matrix goes to infinity of x hat minus x naught. Okay? So I repeat what we're doing. We're given a matrix. It's exactly low rank. I corrupt it with Gaussian noise. I try to estimate the original matrix via doing PCA. I estimate the number of principal components. In this particular case, I'm fixing tau for the time being. And I'm going to find the optimal tau by measuring the following error, which is how close the optimal solution is to the true one, as the dimension of the matrix goes to infinity. And obviously that error is going to change with different choices of tau. Obviously this result is purely theoretical in the sense that in reality I don't know the true x naught, right? So I'm computing the error with respect to the true, but that's not known. So here is the beauty of the theorem. It says that the optimal tau, maybe I should have just said tau there, and this is an error, and that error obviously depends on the So the optimal error, the smallest possible error, is achieved with tau equals to 4 divided by the square root of 3 times sigma. And this theorem is due to Donohoe. And very recent, it's 2014. Now, proving it is well beyond the scope of the class, but I wanted to mention it, of how actually we went from thresholding is something like everyone would do, and it makes sense and it's intuitive, but there is no reason for it to work at all. And I mentioned a lot of potential problems. If you scale the data, it's going to be wrong, and all of that. But as it turns out, if you make assumptions, if data is low rank, you draw the entries at random, you compute this so-called asymptotic mean square error, because that's the sum of the square of the errors, and asymptotic because I'm letting the size of the matrix go to infinity. So as it turns out, if I knew just the standard deviation of the error, I could find the optimal threshold. And let me just conclude there with the chapter. So to summarize, what have we done so far? We have looked at the simplest possible unsupervised learning problem, which is given data in potentially very high dimensional, how do we reduce that data to a few meaningful principal components that then can be used for data visualization or for data interpretation or for data classification. We defined various ways of solving that problem. One was purely statistical, find the direction of the data that gives the largest variance. The other one was geometric, fit a low-dimensional subspace to the data. And the third one was purely optimization-based. It's like, find a matrix that is close to the given matrix that has low rank. And we demonstrated how these three different solutions, three different formulations, give rise to the same solution, and the solution is simply given by the singular value decomposition of the data. At the end of the day, all what you need to do is take the SVD of the data and keep the top D principal components, the top D singular values. Okay? Keep the singular vectors corresponding to the top D singular values. And last, we went through the question of what if I don't know how many principal components. If the task is visualization, typically you would choose 2 or 3, which is as much as you can do. But if the task is classification, you can choose arbitrarily many. And a way to do it is, and the simplest and most intuitive, is just to threshold the singular values. And it turns out that there are theoretical results that justify that thresholding method, and that provide you an optimal estimate of what the threshold should be. Unfortunately, that optimal threshold depends on the amount of noise. So if you do know how much noise there is in the data, then you can choose that threshold. Otherwise, if you really don't know, you can try a variety of information criteria. But all of them also depend on that value of sigma. So if you're a practitioner, how would you try this? You could select a value of sigma that you like, pick whichever of those criteria that you like, and that will give you a guess of what that dimension should be. with that dimension in mind, right, I can now try to guess what the noise level is by looking at how far apart are all the points from that estimated subspace for that dimension. And with that, I could try to recompute that signal, and then repeat the process again to get a better estimate of the dimension. Okay. So, all right. So what I'm going to move now is to chapter 3. Which is PCA with corrupted data. And in particular, I'm going to begin with 3.1, which is PCA with missing entries. Okay. So what's the idea? Everything we've said so far, we assume that the data was given to us. We knew every entry of the data matrix. And we tolerated some noise. In fact, the last theorem says exactly that. You have a low rank matrix and you corrupt it with some small amount of noise. But in reality, that may not be the case. I may not be so lucky. And there are many applications that I motivated in the first lecture in which the data might be corrupted. One of them is the case of data with missing entries. So what are examples where missing entries show up? For example, in the case of face images, right? I could be in a situation where maybe lots of pixels all over the place. Someone went and I don't have the values for those pixels. Or we could have the Netflix example where what we have is that in this direction maybe I have the movies, and in this direction I have the users. Okay? And users only rate a few movies. Maybe this guy rated those 3, this other user rated these other 5, and so on and so forth. So that entire matrix is very sparse. The number of entries that are available to me is very few. And my goal is to be able to, I make the assumption that that matrix is low rank. Why that matrix might be low rank in the Netflix case is because maybe the number of different genres of movies might be 10 or 20. So this matrix might be several million movies and several million users, but the rank of it might be 100. Okay. And so the question is, can I exploit the fact that the data comes from a subspace to be able to complete all of the values that I don't know and estimate that subspace in spite of the fact that the data is corrupted by those missing entries? Okay. So geometrically, what is this problem? There is a true subspace that is there. Let me think of that. Think, for example, right? Let's say this was X, Y, and Z, where, let's say we are in R3. I've got 3 coordinates. Let's say that the plane is the XY plane. But I don't know that it's the XY plane. But what happens then is that if I give you a point, let's say that I only gave you 2 coordinates. So I'm going to give you, let's say, X naught, and I'm going to give you Y naught. And the third coordinate, I don't give it to you. And you don't know. And you don't know what the subspace is either. But you know that that point lies in some subspace. So, in this particular case, because you know X and Y, and you only don't know the Z-axis, this means that each data point that has an unknown entry actually defines a line. Instead of being a point, it becomes a line. Why? Because any Z value is good, right? You don't know. And so your goal is determine out of all possible z values, the one that intersects with the right subspace. And that's how we're going to complete that data point. Okay? So I give you 2 coordinates and I ask you to complete the third. And the way you would do it is by saying, well, this is a line. If I intersect that line with the true subspace, then I'm going to be able to find the extra coordinate that I was missing. Yes?
So in this example, the true subspace has the same number of dimensions as like the original.
In this picture, it so happens, yes, indeed, that the dimension of the subspace was 2, and that the number of observed entries was 2. But in general, this could be different. Maybe the subspace will have dimension 5, and the number of observed entries might be 20. It's just that in a picture in R3, the only numbers I can think of are 1 and 2, so very likely they'll match. Okay, so let's try to formalize this problem a little bit. So suppose that I have a point x, and that point x is a point now in R2. And suppose that x has lots of coordinates, so x1 and xi, and eventually x3. Okay. And I'm going to assume that the ith coordinate is not given. So what I'm going to do is that I'm going to write this point as x1. I'm going to put a 0 in the part that is unobserved, and then a bunch of xd's, plus xi times a bunch of zeros everywhere, a 1, and then a bunch of zeros. Okay. So first of all, do you agree that I can just decompose any point that I want as the point, but I fill in the missing entries with a 0, plus the value of the missing entry that is unknown times a 1. Is that clear? I haven't done much really. So mathematically all I've said is that every data point can be written in this particular case as x, I'm going to denote here as minus I, because I'm going to set the ith entry of it to 0, plus xi times e sub I. E sub I is going to be just the ith basis vector in Rn. Okay? So, what is this? I think the very first time I told you what is a subspace, I said a subspace is a, or actually I told you, let me give you an example of a subspace in a line. I said any line is a point plus lambda times the direction, right? That's what I said the very first time that I introduced what a line is. But that's exactly what's going on here, right? This is a point plus an unknown times a fixed direction. So this is actually the equation of a line. So pictorially, all what's happening is exactly more or less what I just drew in there. Okay? So I've got some subspace. It doesn't need to be the xy plane as I have drawn it over there, right? And these are the axes, so x2, x3, 1, whatever. And this is the equation of a line. There is this line. So that's the direction, p sub I. Okay. That's exactly what I've written here. And this is the true subspace. Now the subspace, we have denoted it in the case of an affine subspace. We have this notation mu plus u times y, where y belongs to R. So that is our notation for the subspace. It's point plus basis times low dimensional representation. The same thing as line is point plus this is the basis and that's the low dimensional coordinate. It's just that this guy is one dimensional and this is the subspace that is little d dimensional. So geometrically, if you were asked to complete this data point, how would you do it? This is the equation of the line. So again, what is the line? I get a line because I'm missing only one entry. Okay, so if I have a point with one missing entry, it describes a line. By analogy, we will see that if I am missing two entries, there will be a plane of possibilities, and so on and so forth. But for now, if there is only one missing entry, it describes a line. Then I go to subspace, and I look at the picture. How do I find that unknown component? Well, I just need to intersect that line with that subspace, right? I need to find a point that belongs both to the line as well as to the subspace. So to do that, I just make these two equations equal. So I get x minus I plus xi e sub I is equal to mu plus u times y. Okay. And from here, I get u minus e sub I times y, and then xi is equal to x minus I minus u. Aha. So, what are things I'm assuming in this particular case I know? I'm actually telling you, let's assume, it's fictitious, it's not true, but let's assume that I knew the subspace. So I have the basis. I know the missing direction, right? I know which entry is missing, so I can generate the ith column of the identity there. I know the data point that is given to me, except for the entry that I don't know. So this is, I just fill in with 0. And I know the mu, which is the point in the subspace. Okay, so this quantity is known, this quantity is known. So what is it that I don't know? I don't know the low dimensional coordinates, the projection of the point on the substrate, and I don't know the missing entry that was not given to me. Okay. So can I compute y and x sub I? Well, yeah, this seems like a linear system where the dimensions, this seems to be, is d rows, and the number of columns, what is the number of columns? Huh? D plus 1, right? Which is the same as the number of unknowns, because it's really y is the low dimensional subspace dimension, plus the missing entry that I don't know. So that's the number of unknowns. So, what are the conditions under which this linear system can be solved? Basic linear algebra, if I give you an equation ax equals b, when is the solution unique? A is invertible. Okay. We are in a situation where we tend to assume that the dimension of the data is really, really big, so we expect this matrix to be sort of tall, right? Actually, does it mean that A is invertible really? Cannot be invertible because it's not squared. So the rank needs to be at least d plus 1. So we need the rank of u and minus e sub I to be d plus 1. Now I know that the u is a basis for the subspace, so that I know already is rank d, right? So what are the only possibilities for the rank of this matrix? I take a matrix U that has rank D, and I add an extra column to it. What can happen to the rank? It either stays the same, or it increases by 1. All right? So, I would like the rank to increase by 1. In that case, I would be able to complete the missing entry. So, I'm just asking when this fails. When can I cannot complete the missing entry?
It's dependent on the column with Q.
Okay. But in particular,
One of the columns with Q is E sub I.
one of the columns of U is
E sub I.
E sub I. Okay, sure, that would be a failure case, but that's too extreme. I'm
Yeah.
looking for the exact condition.
If the I can be represented in terms of linear combinatorial basis or something.
Okay, right. So if E sub I belongs to the span of U, then the rank will be D. So in that case, it would fail. Okay. So if the ith direction is a linear combination of the columns of the subspace, then it would fail. I would not be able to recover. Pictorially, right? Think about, this subspace is there and is moving. Which would be a case that you cannot tell? Exactly where the line belongs to the subspace, right? That's exactly it. This is just algebra for that geometric picture that, So in a sense, this is a trivial and almost stupid example that I'm doing, but in the next lecture, I'm going to start writing incoherence conditions of blah, blah, blah matrices that have become very abstract, but I want to build the intuition today. You can complete the entries in some cases, but in other cases you cannot. And whether you can or cannot depends on how the missing entries are, or where the missing entries are relative to the subspace. Okay? And the buzzword that I'm going to introduce in the next lecture is that the missing entries, and I'm being very vague here, but the missing entries need to be incoherent with respect to the basis of the subspace. I'll make that very precise in the next lecture, but I hope this contains the gist. Okay. So, a necessary condition for me to be able to reconstruct the data point and find the missing entry here is that the missing entry, the vector corresponding to the missing entry, does not belong to the span of the subspace. More generally, let me now do it with multiple missing entries. So suppose now that I have the vector x, and now there are many entries that are missing. Okay? Without loss of generality, I'm going to assume that all of the unknown entries are at the very top, and all of the observed entries are at the bottom. Right? I'm just going to reshuffle the entries so that this is the case. So, as before, I can write this guy as 0 x observed plus the identity 0 here times x right? X unobserved. All right. So I am going to m here is the number of missing entries. Okay. So effectively, what I'm saying is that this vector is of dimension m, and the number of observed entries is d minus m. Okay.
XU multiplied by m.
XU multiplied by
Shouldn't that be reversed?
1. No, what I'm saying is that, maybe I shouldn't have continued there. XU is a vector of dimension m times 1, and x observed is of dimension d minus m times 1. I'm saying, this is the identity matrix, M by M, multiplying U, which has dimension M. So that goes there, plus 0, you get that. So see, it's the same decomposition that I wrote over there, but fancy, right? I wrote x minus I. What was x minus I? It was the same data x, but with zeros in the missing entries. That's exactly this guy, right? I keep the observed, and I set to 0 all of the unobserved. And then I wrote a scalar times the direction that is missing. This matrix here is exactly now the matrix whose columns have all of the missing directions. Right, the is of i's. This is the matrix with all of the is of i's. And these are just the coordinates that are missing. Okay? So by analogy with what I did before, now it needs to be equal to mu plus s, exactly what I wrote there, exactly equal to mu plus u times y. But I'm going to split it in the same order. It's going to be the part of mu that corresponds to the unobserved vectors, the part of mu that corresponds to the observed. I'm also going to do the same with u unobserved and u observed, and then the y. So, in the same way that I just solved, what do we get? We get, let's see what we get. U unobserved minus I sub m times y times x unobserved is equal to, let's see, u times y plus minus that is equal to, I think, minus mu unobserved. And then at the bottom, I'm going to get u observed. Then the xu is not there, right? Yeah, so 0. And then what's left is minus mu unobserved. And I should be missing something, and the x observed, right? All right? That's the equation. Okay, let's just double check that more or less things are what they're supposed to be. See, before it was u, and then augmented by a column that has zeros and ones corresponding to the missing entries. Now we're getting more or less the same. This is just the U matrix here. And now I've got a matrix of ones and zeros that specifies which entries are missing and which entries are not. Columns of the identity associated with the missing entries. And now the only difference is that I've got m of them as opposed to 1. And the equation is the same, low dimensional coordinates, but now I've got to also compute the number of missing entries. And the dimension of this matrix is now d times d plus m. Right? Correct? Good. On the right-hand side, what did I have before? It was the data point with the missing entry set to 0 minus the mu. That's exactly what I have here, right? Is the data point with the missing entry set to 0, and then I subtract mu. So it's the same. No change. So now I'm going to ask the same question. What is a necessary condition for me to be able to complete all of the missing entries? And what we need is that the rank of this matrix that has the u, u0, and minus I and 0, the rank needs to be equal to in order for me to be able to complete it? Huh? D plus M. Right? So I need the rank to be D plus M. Now, by construction, this matrix is supposed to be tall, so the number of columns needs to be less than or equal to the number of rows. Right? So the first thing that is being said here is that, as before, I'd like the directions corresponding to the missing entries not to belong to the span of U. So it's just a generalization of the same statement I made before. Missing entries and bases of the subspace need to be somehow linearly independent. But the other part that I wanted to make is just a counting argument. But based on this inequality that I just wrote there, it says the following. D minus M needs to be less than or equal, bigger than or equal to D. And what is this? This is the number of missing entries. This is the total number of entries. So the difference between the two is the number of observed entries. Needs to be bigger than or equal to D. Okay, it better be that the case. I mean, it's sort of very intuitive that, you know, I can accept some entries that are missing, but I need to observe at least as many as the dimension of the subspace. Okay, coming back to the Netflix challenge example, if there are 100 genres, and so the dimension of the subspace is 100, I would like every user to rate at least 100 movies to get this right. Okay? Maybe not. Maybe the rank is even lower so that this works. Okay? But that's the intuition. I need to observe sufficiently many entries if I want this to work. Okay. Thank you very much. See you on Friday.